Imagine a world where the very fabric of reality is not as fixed and tangible as we once thought. Picture this: you have two marbles, one red and one blue. Now, no matter how far apart you take them, across a room or even across an entire city, the moment you touch the red marble, the blue one instantly changes color too. It's like magic, isn't it? But what if I told you this wasn't just a trick of the mind but something profoundly real and scientifically proven? Quantum entanglement is one of those concepts that seems almost impossible to grasp fully. Imagine two particles so intertwined with each other that their properties are linked no matter how far apart they are in space or time. Albert Einstein famously referred to it as spooky action at a distance. He couldn't quite wrap his head around the idea, but he was intrigued enough to spend decades trying to debunk it. Let's travel back in time to 1935 when Einstein and his colleagues Boris Podolsky and Nathan Rosen proposed what is now known as the EPR paradox. They were questioning whether quantum mechanics could truly be a complete theory of nature or if there was something else at play, hidden variables perhaps, like an invisible thread connecting these entangled particles. But then came John Bell in 1964. He developed a way to test Einstein's idea experimentally by coming up with what we now call the Bell inequality. This mathematical framework allowed scientists to conduct experiments that could either prove or disprove hidden variables. And guess what? The results were astonishingly clear: entanglement was real, and it defied all common sense. Fast forward to today, where researchers are not only confirming these quantum phenomena but also exploring their practical applications. Think about how this might change our world if we could harness the power of entanglement for communication or computing. Imagine sending messages instantly over vast distances without any loss in quality, like having a conversation with someone in the heart of a bustling city. We find ourselves among the towering skyscrapers that seem to stretch toward an endless sky. Yet, amidst this concrete jungle, there's something far more mysterious and abstract waiting just beyond our everyday perception, something so strange and counterintuitive that it has intrigued scientists for decades: quantum entanglement. Imagine a world where two particles are connected in such a way that the state of one particle instantly influences the other, no matter how far apart they are. This connection defies all classical notions of space and time, challenging our very understanding of reality itself. It's like whispering to someone on the opposite side of Earth without even touching your lips. Quantum entanglement is a phenomenon that emerged from the strange predictions made by physicist Werner Heisenberg in his formulation of quantum mechanics back in the 1920s. At first, it was considered too bizarre and abstract for practical use. But over time, as experiments became more sophisticated, this enigmatic idea began to take shape. In a laboratory, scientists use special equipment like lasers, crystals, and superconducting magnets to create pairs of entangled particles. These particles could be photons or electrons. Their states are so intertwined that if one particle is measured in any way, the state of its partner will change instantaneously, no matter how far apart they might be. To understand this better, let's visualize a simple experiment. Imagine two identical coins placed far apart from each other on opposite ends of a room. Each coin can either land heads or tails when flipped. In classical physics, if you flip one coin and it lands heads up, the outcome of flipping the second coin is completely unpredictable. You have no way to know what will happen until you actually do the experiment. But in quantum entanglement, things get much stranger. Let's say we prepare these two coins so that they are entangled. If one coin comes up heads, the other must come up tails, and vice. The world of quantum mechanics is a fascinating mystery wrapped in logic and science. Today, we delve into one of its most intriguing concepts: quantum entanglement. This phenomenon challenges our understanding of the universe by connecting particles no matter how far apart they are, as if they share an unbreakable bond. Imagine two tiny specks floating in space, each with their own unique properties and behavior. Now, picture these specks suddenly linked together in a way that defies all known physics. Change something on one speck, and the other reacts instantly, no matter how far apart they are. This is quantum entanglement, an idea so bizarre it's hard to grasp at first glance. Scientists discovered this strange connection almost by accident. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen proposed a thought experiment known as the EPR paradox. They imagined two particles that were inextricably linked. Changing one should affect the other instantly, even if they were light years apart. This sparked a debate between Einstein's skepticism and Niels Bohr's more radical acceptance of quantum mechanics. Einstein famously referred to entanglement as spooky action at a distance. He couldn't accept that particles could be so deeply connected without any physical means of communication. Yet, experiments over the years have shown that this connection is real and incredibly precise. Quantum entanglement isn't just a theoretical idea, it's an observable fact. To understand how quantum entanglement works, let's take a closer look at what happens when particles interact in such a way. When two particles are created together, like during the decay of radioactive elements, they can become entangled. Their properties become linked so that any change to one particle instantly affects its partner, no matter where it is. This phenomenon was first observed experimentally by Alain Aspect and his team at the University of Paris in 1982. They used photons, particles of light, and showed in the heart of a vast cosmic playground where billions upon billions of stars dance under their own laws of physics lies a phenomenon so bizarre that it defies our most cherished notions of reality. This is quantum entanglement, a concept that challenges everything we think we know about space and time. Imagine two particles, perhaps photons or electrons, paired in such an intricate way that the state of one instantly influences the other, no matter how far apart they are. Albert Einstein famously referred to this as spooky action at a distance. But what makes quantum entanglement truly mind-bending is not just its complexity but also the way it blurs the lines between our classical and quantum worlds. Let's dive into the heart of this mystery, starting with the basics. A pair of particles can be created in such a state that their properties are correlated in ways that cannot be explained by classical physics alone. For example, if two electrons form an entangled pair and one is spinning clockwise while the other spins counterclockwise, changing the spin direction of one electron will instantly affect its partner on the opposite side of the universe. To understand this better, let's consider a more tangible analogy. Picture you and your twin separated by vast distances. When something happens to one of you, say, you start wearing a red shirt, the other immediately starts wearing a blue shirt as well. It doesn't matter if you're on different planets or even galaxies, the change in one is instantly reflected in the other. This instantaneous connection defies our everyday experience and challenges our understanding of causality. The concept was first proposed by physicist Erwin Schrödinger, who described it with a famous phrase, "The entanglement creates a remote action between two particles." But why does this happen? What is the mechanism behind such an inexplicable phenomenon? One explanation comes from quantum mechanics, which suggests that when particles become entangled, they share information in a way that transcends conventional spatial and temporal boundaries. The concept of quantum entanglement is one that defies our everyday experiences. In the world of classical physics, objects are separate entities, each following its own path governed by forces like gravity or electromagnetism. But in the realm where particles interact at microscopic scales, these rules seem to break down. Imagine a pair of socks. When you put them both into your laundry basket, they remain distinct and individual items. They don't affect each other's color or size unless some external force acts upon them. This is how we usually perceive objects in our daily lives. Now, consider two quantum particles, let's call them particle A and particle B. In the world of quantum mechanics, these particles can become entangled. Once this happens, their states are no longer independent. A change to one particle instantly affects its partner, regardless of distance separating them. This connection persists even if they're on opposite sides of the universe. This phenomenon was first observed by Albert Einstein and his colleagues Boris Podolsky and Nathan Rosen in 1935 through what is now known as the EPR paradox. They described entanglement as a spooky action at a distance, emphasizing its eerie nature, which contradicts our intuitive understanding of reality. Quantum entanglement has profound implications for various fields beyond just theoretical physics. In cryptography, it holds potential to create unbreakable codes and secure communication channels against eavesdropping. Imagine sending messages that could not be intercepted or altered without detection because any attempt at interference would instantly affect the message recipient in a way that reveals tampering. In computing technology, quantum entanglement is paving the way for more powerful computers called quantum computers. These machines use qubits, quantum bits, instead of classical bits to process information. When multiple qubits become entangled, they can perform complex calculations much faster than traditional computers. This could revolutionize fields such as drug discovery, climate modeling, and artificial intelligence by solving problems that are currently beyond the. As we stand at the threshold of understanding quantum entanglement, it's hard not to feel a mix of wonder and skepticism. This phenomenon challenges our very notions of reality. How can two particles be instantly connected across vast distances? It seems almost magical, yet every piece of evidence points towards something deeply logical and profound. But let's pause for a moment and look at this through the lens of logic and analysis. Quantum entanglement isn't just about spooky action, it's fundamentally tied to how the universe operates on its most fundamental level. The laws that govern these tiny particles are not arbitrary, there is an order, even if we can't fully grasp it yet. Imagine you're holding a pair of dice, one in each hand. You shake them and without looking, you throw both at the same time. One lands with a 6, and just as mysteriously, so does the other. This isn't because there's some hidden mechanism linking your hands, rather, every possible outcome was encoded into those dice from the moment they were created. Quantum entanglement works in much the same way, but on an infinitesimally small scale. The states of these particles are intertwined at birth, and only when we measure one do its partner's properties become apparent. This doesn't mean magic is happening, it means that our understanding of space, time, and causality might need to be expanded. Now, consider the implications for technology. If we can harness this phenomenon, imagine the possibilities. Quantum computers could revolutionize data processing in ways we can barely fathom today. Secure communication networks would become nearly unbreakable. The world as we know it could fundamentally change if only we learn how to work with these tiny particles. Yet, every breakthrough comes with its own set of challenges. We're still grappling with the mechanics behind this phenomenon. Why do entangled states collapse when measured? How can information travel faster than light without breaking relativity's laws? These questions hint at not all mysteries have answers, but we keep searching. Subscribe to join the hunt.